So now we talk about properties of fluids. The first important property of fluid is mass density. Now mass density is defined as, now the symbol is rho. Now it is defined as mass of fluid per unit volume. Okay, so the formula for rho is m upon v. Now its SI unit is, so for mass the unit is kg and for volume the unit is meter cube. So this is its SI unit for mass density. So the greater is the value of rho, it is difficult for a fluid to flow. Okay. Now the density of water is 1000 kg per meter cube. Okay. The second important property of fluid is specific weight. The symbol is small w. Now it is defined as weight per unit volume. So you can say specific weight is defined as weight of fluid per unit volume. Okay. So W we can write as, the formula is weight divided by volume. Now its SI unit for weight is Newton and for volume is meter cube. So this is Newton per meter cube. Okay. Now the other name of the specific weight is weight density. So from this formula, now we can write as, now weight is, so W you can write as weight is m into g, mass into acceleration due to gravity divided by volume. So m upon v is rho. So W we can also write as rho g, or rho you can write as W upon g. Okay, so this is specific weight or weight density. Then the third important property of fluid is specific volume. The symbol is small v. It is the volume of fluid per unit mass. So you can write V as volume upon mass. SI unit for volume it is meter cube, and for mass it is kg. So you can also see this is inverse of mass density. So this is specific volume. Then another important property of fluid is specific gravity. The symbol is S. Now this specific gravity has three definitions. One is the general definition, second is the definition for liquid, and third definition is for gases. Okay. Now the general definition for specific gravity is, it is the ratio of the specific weight of a fluid to the specific weight of a standard fluid at standard temperature and pressure. Okay. Now this is the general definition. So you can write as S is equal to specific weight of specific weight of fluid divided by specific weight of standard fluid at standard conditions. Now if we talk about liquid, for liquid, now the definition becomes the ratio of the specific weight of a liquid to the specific weight of a standard liquid at standard temperature. Now for liquid, the standard temperature is 4 degrees centigrade and pressure is 1 atmospheric pressure. So you can say the ratio of specific weight of a liquid to the specific weight of a standard liquid at standard temperature, that is 4 degrees centigrade, and at standard pressure, that is 1 atmospheric pressure, is the specific gravity of a liquid. So specific gravity of a liquid is specific weight of liquid divided by specific weight of standard liquid. Now standard liquid is water at 4 degrees centigrade and 1 atmospheric pressure. Okay. Now in case of gases, now this definition becomes the ratio of the specific weight of a gas to the specific weight of a standard gas at standard temperature, that is 15 degrees centigrade, and pressure, that is 1 atmospheric. So that becomes the specific gravity of a gas. So S for a gas we can write as W for gas divided by W of a standard gas. Now standard gas is either air or it will be hydrogen. Okay, so that becomes the definition of specific gravity. Now, specific gravity S you can also write as, now if we talk about the general term, that is equal to, now specific weight of fluid we can write as rho into g of fluid. Now specific weight of water we can write as rho into g of water or standard fluid. Now this becomes, now g is constant, so this becomes rho for fluid divided by rho for standard fluid. So you can also say specific gravity is the ratio of densities, density of fluid to the density of standard fluid at standard conditions. Now, because of this relation, S is equal to rho F divided by rho of standard fluid, we can also call this S as a relative density. The another name for S is a relative density. So another name for specific gravity is a relative density, because this is also the ratio of densities, density of a fluid to the density of a standard fluid. Okay. Then another important property of fluid is, that is fifth one, viscosity. Okay. So let us say we have a flowing liquid. So that liquid is flowing in layers, something like this. And if we talk about two successive layers, so this is one layer, this is the second layer. Now in this layer we have the molecules, molecule of liquid. This layer also have the molecule of liquid. When this liquid is under flowing condition, then what happen? The molecules of lower layer try to push back the molecules of upper layer. So you can say there is existence of resistance due to flow. And the measure of that resistance we can term as viscosity. Okay. Now let us say the bottom layer is moved with some velocity u. The upper layer is moving with some velocity u plus du. The distance between these two layers is say dy. Okay. Now if we talk about from the reference or from the bottom surface, the distance of lower layer is y and the upper layer is y plus dy. Okay. Now we can write a tau, the resistance force per unit surface area between the two layers, that we write as tau. Now this tau is shear stress between these two successive layers. So tau we can see is proportional to the difference in the velocity of layers and inversely proportional to the distance between two layers. So tau we can see is proportional to du by dy. Now this du by dy, this is also called rate of change of velocity with respect to y, or we can also call it as velocity gradient. Okay, so now you can write tau with an equality sign equal to a constant of proportionality du by dy. So this constant of proportionality mu, we call it as viscosity or dynamic viscosity. Okay, and this equation is known as Newton's law of viscosity. So as we earlier studied, the fluids which obeys Newton's law of viscosity, that we call as Newtonian fluids. That we call as Newtonian fluids. Now next we try to define the term mu, the viscosity. Now from this relation, you can write mu is equal to tau divided by du by dy. Okay. Now say if we consider a vertical element dy, say this is our vertical element dy. Okay. If upper end will move a distance du with respect to lower end in 1 second. Now say this upper layer of this element moves by a distance du with respect to the lower layer in 1 second in a unit time. Then you can say the term du by dy is the angular displacement, or we can call it as deformation. So now you can define mu easily, or mu is dynamic viscosity or simply viscosity. So you can write it as viscosity can be defined as the shear stress required to produce unit rate of angular deformation. So that is viscosity. So viscosity is defined as shear stress required to produce a unit rate of angular deformation. So that is mu. Okay. Then next we see the effect of temperature on viscosity. Okay. So for gases, viscosity increases with increase in temperature. For liquid, viscosity decreases with increase in temperature. So why this happens? Now the reason behind this is, now in case of liquid, we have different molecules. So say these are different molecules within the liquid, and within these molecules there is some force of attraction. So that we call as cohesive force. Okay. So when we increase the temperature, this cohesive force, that is the force of attraction between the molecules, it decreases. So due to that, mu decreases, viscosity decreases. So that is the reason behind the decrease in viscosity with increase in temperature in case of liquids. Now in case of gases, there is no concept of, in case of gases, there is no concept of cohesive force. So there is a large distance between the molecules of a gas. So when we increase the temperature in gas, what happens? The momentum of molecules of that gas also increases. So due to increase in this momentum, the molecule starts moving, their velocity goes on increasing, and they strikes with each other. They strikes with each other with more faster rate. So due to that, when gas flows, this striking of molecule reduces their chances of flow. So that reduces the chances of flow. So that resists inflow. So that means in case of gases, when we increase the temperature, viscosity also increases. The resistance to flow also increases. Okay. So this is the effect of temperature on viscosity. Then next we see the units, the dimensions of viscosity. So now you can write mu. Mu is tau du by dy. Now the unit for tau is stress Newton per meter square. Du is the velocity meter per second, and for distance it is meter. So you can write it as Newton second upon meter square. Now further, Newton is the force, mass into acceleration. So we can write it again as Newton is mass, mass for mass unit is kg, acceleration is meter upon second square into second divided by meter square. So we can write it as kg upon meter second. Kg upon meter second. Okay. So when we talk about the CGS unit, for kg it becomes grams, and for meter it becomes centimeter per second. So CGS unit for mu is grams per centimeter per second. Okay. So this CGS unit for viscosity we call it as poise. Okay. So 1 poise we can write as equal to, so 1 poise we can write as equal to 1 gram per centimeter per second. Okay. Then 1 centipoise. So that is 1/100th part of poise. That is centipoise. Now we have one more type of viscosity that we call as kinematic viscosity. The symbol is nu, and it is the ratio of dynamic viscosity to the mass density. If we talk about its units, mu having unit as kg per meter second, the O has kg upon meter cube. So for mu, the unit becomes meter square per second. Its CGS units, centimeter square per second. So 1 centimeter square per second, that we call as 1 stoke. Okay, then we have 1 centistoke, that is 1/100th part of stoke. That is 1/100th part of stoke. Okay, so these are some properties of fluids. We have 2 or 3 more properties that we discuss in next class. Okay, thank you.